In this tutorial, we are going to create an automatic ladder. Let's take a look at the finished result so you know what you will be making. With this bone, you decide what the ladder is leaning against. If you place it right by a wall, the ladder will lean against it. This second bone moves the base of the ladder. Notice how the ladder continues to lean on the wall when I move it. And if I move it too far from the wall to be able to reach, it lies flat on the ground. The third and last bone is the master bone, used to move the entire ladder around. That's it for the placement. To the right in the object panel, we have a few sliders that changes the look of the ladder. Let's try them out one by one. Most of them are self-explanatory. First we have end distance. As you can see, this changes the length of the top and bottom. Next we have the step count, the number of steps. The step depth. Step distance. Step height. Step width. Support depth, the depth of the support beams. And finally, support width. So, that's it. Let's get started. We will begin by modeling one segment of the ladder, which is one single step. That way, we can later add an array modifier and easily set the length of the ladder to anything we want. One step, repeated multiple times. We will start by creating the support beams, the sides of the ladder. First, we will remove the camera and light. Take the default cube, enter edit mode and scale it 0.5 along X and Y so we get a 2 by 1 by 1 block. Then, move it 1.5 units along X so it is placed 1 unit from the center. This way, the entire mesh is on one side of the origin point. If we now add a mirror modifier, you can see that we have the two sides of the ladder. This way, we will only have to change one side when we are modeling. We could easily mirror it along Y and Z as well, since it will be all symmetrical, but that won't actually help us in our modeling. When we have a loose block like this, we can easily select the entire block and scale it in different ways. Mirroring it in more axes will only introduce more geometry, making the viewport and render slower. Now we will create the actual step between the sides. Let's duplicate the block and move it 1 unit towards the center. The reason we create a separate block for the step instead of just extruding the side is to make them completely independent. By having them connected, it limits the freedom of different shapes, since the shape of one will affect the shape of the other. Let's scale it 0.5 along C. By making the step 1 unit high and the sides 2 units high, we will get some space between each step when we repeat them using the array modifier to create the entire ladder. Let's add an array modifier so you can see what I mean. Change the relative offset from X to C and set the count to 8. Now we have a basic ladder. Note that the goal is not to create a pleasing looking shape, which will be done through shape keys later, but to create an even and good mesh to modify and do math on. By keeping the length of the sides at whole numbers, preferably at 1, any calculations involving the size will get much simpler. Whenever you use a mirror and/or array modifier, it is good practice to remove any faces that connects to the duplicates. That way, we avoid faces inside the resulting mesh, which can create different problems depending on the situation. Go to wireframe view. This way you can clearly see all the faces even with the array modifier activated in edit mode. Switch to face select mode, select the faces, and delete faces. Activate merge in the array and mirror modifier so everything sticks together. Now we get a clean and good mesh. Let's rename the object to ladder while we're at it. Now let's add the shape keys so we can adjust the shape of the ladder to our liking. Let's go back to object mode and add the first shape key. I will call it step height. For this one, we want to enter edit mode and just change the height of the step. By just changing one single thing in every shape key, we can control every aspect of the ladder independently. Select the step part and scale it 2 along C. If we now go back into object mode, we can adjust the step height using the shape key. By changing the minimum range to -1, we can go all the way down to 0 thickness. That is because the original thickness was 1 and the shape key holds a difference of 1. 1 minus 1 equals 0. Now we have the ability to make it as thin as we want. Let's add another one and call it step depth. Enter edit mode and scale it 2 along Y. When we set the value to -1, we get 0 thickness. Let's continue. The next one will be called step width. This one is a bit different for 2 reasons. First is that it is affected by the mirror, and the second is that this shape key affects both the step and the support part of the mesh. What we want to accomplish in this shape key is to double the width of the step. To do this, we need to move the one side of the step and the support 1 unit along X. So, switch to vertex select mode, grab everything except the vertices in the center and move them 1 unit along X. This way, the step becomes 4 units wide, or twice as wide as before. If we adjust the minimum range to -1, we can, just like before, change it all the way down to no thickness. Next up is step distance. To make the distance between the steps longer, we will simply increase the length of the sides of the ladder. Select the side and scale it 2 along C, and set the minimum range to -1. Then we have support depth. Just scale the side 2 along Y, and change the range. Finally, we have support width. This one is a bit different as well. We don't want the width of the support to affect the width of the step, so it can only grow outwards, away from the center. Switch to face select mode, select the side of the support and move it 1 unit along X, making it twice as thick. Now the width of the support only affects itself. Set the minimum range to -1. Notice that we have created a total of 6 shape keys. This is not a coincidence. What we have in our mesh is 2 separate blocks, the step and the support, and these blocks can be scaled in 3 different dimensions. Our 6 shape keys are the X, Y and Z change of 2 objects. C of step, Y of step, X of step, C of support, Y of support, and X of support. It is clear that we have created one shape key for every possible change. Now we are sure that we have created all the different shapes we need. Instead of changing the value of the shape keys directly with these sliders, we will add custom properties and control the values through them. There are 2 reasons for doing this approach instead of just changing the shape keys directly. The first one is that we can have all of our controls collected in one place, being able to adjust everything about the ladder, even things that aren't shape key related, without having to move around in the interface. We will get to the second reason a bit later in the tutorial. Since we will be using an armature to position the ladder later, it is a good idea to add the custom properties to that armature. That way, all the controls will be in the same place without the need of switching objects. So, to be able to add our custom properties, let's add an armature first. Add armature, single bone. With the armature still selected, we will start adding our custom properties. Go to the object panel. Let's pull the custom property panel to the top so it is easier to reach. Now I will go through and add one for every shape key we created earlier. Each one of these will control the corresponding shape key. I will give them the same name as the shape keys to make it easier to remember. To make these values actually affect the shape key we set up, we will have to add drivers to the shape keys. Go to the shape keys, add a driver to the first shape key, step height, and open the graph editor, drivers. Click on the key and open the properties. We will let the variable name remain as var. Change it from transform channel to single property. Select our armature and write the path. As for the scripted expression, I'm actually going to set it to var -1 instead of just var. That way, when the custom property step height holds a value of 0, the shape key step height will get a value of -1, creating a thickness of 0. A property value of 0 gives a thickness of 0. That is much easier to understand than having the control starting at a value of -1. If we go back to the custom properties and test, we can see that the step height property now affects the height of the step. Currently, the custom properties can only hold a value between 0 and 1, which is very limiting. Let's change the maximum value to 10 on all of the custom properties so we have the freedom to create very extreme ladders. Since all of the limiting of values will from now on be done through our custom properties, let's go to the shape keys and increase the range to the maximum. Otherwise, we might end up with a situation where changing the custom property won't affect the mesh because the value is being limited by the shape key. Note that the maximum range of a shape key is 10, so giving the driver a higher value than 10 will give no effect. If you wish to create a shape key that has greater effect than this, you would have to make the actual shape key stronger, moving the vertices say 10 units instead of 1 inside the shape. However, in this case, a maximum change of 10 units is more than enough. Currently, we have only added a driver to step height, so we will have to add one to all the other shape keys as well. Let's copy the driver from step height and start pasting it to all the other shape keys. If we now go to our driver window, we can easily change the data path of every driver to the correct custom property. And that is all we need to do. If we go back to our custom properties, we can see that all of these controls are working like they should. However, I would like the value of the controls to directly reflect the size of the shape we create. This is already the case for most controls. Step depth has a depth of 0 units when the control is at 0, 1 unit when the control is at 1, and 3 units when the control is at 3. However, there are 2 controls that don't behave like that. First is step width. It is twice as wide as it should be since it is doubled by the mirror. A value of 1 gives us a width of 2 units. We can easily fix this by adjusting the driver. Select the step width driver and change the expression to var divided by 2 minus 1, making the value from the control half as big. And now a value of 1 gives the ladder a width of 1. The second shape we need to adjust is step distance. It has the same problem of being 2 units at a value of 1. So let's change the expression in the same way to var divided by 2 minus 1. Now the ladder looks like a solid block, so let's increase the step distance and step width controls to 2 so it looks like before. Now all the values of the controls reflects the actual shape. Let's add a custom property for our number of steps as well. This will drive the count in our array modifier. Name it step count and change the maximum of steps to say 200. Now let's add the driver to the count in the array modifier. We can just paste the driver we have already copied. Change the data path to step count and set the expression to just var. If we now test our step count property, you can see that the ladder gets longer and shorter when we drag the slider. However, it is not possible to have 2.86 steps in a ladder. It is either 2 or 3. We can make it impossible to have anything other than whole numbers by clicking Edit and removing the decimals from the property value. Click OK. Now the custom property only allows whole numbers. So, with all of the basic look controls complete, let's adjust all of our values so it looks more like a real ladder. Something like that will do. One problem with the ladder as it is right now is that it has no top or bottom. You can see right through it. So what we need to do is to create 2 caps for the array modifier. One start cap and one end cap. What this means is that we will create 2 different meshes that will cover each end of the ladder. To create these, we will use the ladder we already have as the basis. Copy it and move it along X. Let's rename it to ladder top right away. Now we come to the second reason why it is good to use drivers instead of controlling the shape keys directly. By doing so, you remain in control of your objects even if they are copied. Note that I did a normal copy, not a linked one. This ladder does not share any data with the original ladder, and yet the ladders remain identical when I adjust the controls. This is because the drivers gets copied with the new object. The shape keys of the copy still has drivers that tells them to listen to the custom properties. Doing a normal copy instead of a linked one is important in this situation because I don't want them to share the mesh data. I want to be able to add and remove vertices from the start and end cap without changing the main ladder. So let's start with the end cap. We just want it to be one step long, so let's remove the array modifier. The driver for the count of the array modifier wasn't removed automatically. It is still here in the list of drivers. It just got disconnected and stopped working, as you can see by this red line. Since we don't need it anymore, we can just delete it. Now go to edit mode, switch to edge select mode, select the top and fill it. If we now add this ladder top as the end cap in our array modifier of the ladder, you can see that the ladder now has a real top. Let's do the start cap the same way. Copy the ladder and move it along X. Let's rename it right away. Ladder bottom. Remove the array modifier and the driver that gets left behind. Enter edit mode and fill the bottom. Then select the ladder and select ladder bottom as the start cap for our array modifier. We now have a complete mesh. The only reason the start and end cap has the geometry for a complete additional step instead of just a single face to seal the hole is that I want to be able to set the length of the ends independently to the distance between the steps. Thanks to the top and bottom being separate meshes, I can now easily change their shape keys and drivers so they can be controlled independently. Let's add an end distance property to the armature and change the maximum to 10 so we have something to control them with. Let's start with the top. I don't want this upper part, the actual end, to be affected by the step distance control anymore, so let's remove that change from the step distance shape key. We do this by simply selecting the step distance shape key, entering edit mode and moving the top vertices 1 unit down back into the same place as in the bases. That way, this shape key won't affect those vertices anymore. If we now change the step distance control, you can see that it only affects the lower part of the top. Now the upper part of the top is free to be affected by another control, the end distance. Let's add a new shape key, name it end distance, and increase the range to maximum. Enter edit mode and move the upper part 1 unit up, the same change step distance held before. Copy and paste one of the other drivers and change the path so it uses the new end distance property instead. Now when we test the end distance control, you can see that it works like it should. The end distance affects just the end of the ladder, while it is unaffected by the step distance. Let's repeat it for the ladder bottom. Select the step distance shape key and remove the change. Add a new shape key called end distance, increase the range, and add the same shape difference here instead. Paste the driver, and finally change it to use the end distance property. And that's it. Let's try using the controls to make sure everything works. Both ends are controlled by the end distance, like they should. We can now move the ladder top and ladder bottom to another layer, hiding them. We won't be touching them anymore. Since the caps now add 2 steps to the ladder that wasn't there before, we will have to adjust our step count control. Currently it says 6 steps, but the ladder actually has 8. To fix this, we can just change the driver to var -2, and now it matches. A step count of 6 gives us 6 steps. However, the range of the step count control is not correct. The lowest count an array modifier can have is 1, And the caps adds 2 steps, so the ladder can never be shorter than 3 steps, no matter how low value the driver gets. If we set the step count control to 0, the ladder still has 3 steps. To avoid confusion, we should set the minimum value of the step count to 3. That way, we can't select a value that is impossible. Now the shape of the ladder can be controlled completely. One issue that still remains is that the ladder goes through the ground floor. Let's add a plane and scale it up so we can see it more clearly. The ladder should always be on the ground plane, no matter what shape we give it. But since the end distance and step distance adds geometry below the origin point of the ladder, this is not the case. So to fix it, we need to raise the ladder the same amount as the end distance and step distance puts it below ground. Since this is an issue about position and not shape, I will use a bone to adjust it. I could just drive the position value of the ladder directly, but I prefer the way everything gets organized by separating it from the ladder. So, now we will start using the armature we added earlier. I prefer the B-bone style, so I will change to that. It just changes what the armature looks like, nothing else. The way we are going to do this is to parent the ladder to our bone and then move the bone to correct the floor penetration. Enter Edit mode, select the default bone and rename it Floor Fix. Go back to Object mode, select the ladder, Shift select the armature, switch to Pose mode, select your bone and parent it. Select bone. Now when I move the bone, the ladder follows. Let's add a single driver to the Y location of the bone, the way that is up for our bone, so we can correct the location of the ladder. Since we know that step distance and end distance are the properties that causes the problem, we know that we will need them in this driver, so we can add them right away. So, how much should the floor fix bone move in relation to the step distance and end distance? What is the correct expression? By looking at the ladder, we can see that it is penetrating the ground by 1 step distance and 1 end distance. So the expression needs to be 1 step distance plus 1 end distance. We don't need to make any other adjustments, thanks to the values of our custom properties being the same as the actual numbers of units in the viewport. This is one of the beauties with having the value of the control directly reflect the resulting shape. Since the needed expression is step distance plus end distance, we can just pick some values instead, since it gives us the sum of our 2 variables. And now the ladder stays on the ground no matter what length I give it. Now it is time to give the ladder the ability to lean. Let's enter Edit mode and add another bone we can use to rotate the ladder. Move it 2 units to the side so we can see it more clearly. Rename it Rotation. If we now parent our floor fix bone to the rotation bone, keep offset, the ladder rotates with the rotation bone. And the floor fix continues to work even at an angle, since it is raising the ladder straight up in relation to its parent, the rotation bone. Now when we rotate the ladder, we notice another type of floor penetration. If we change the support depth slider, we can see that it is the cause of the issue. When it is at 0, there is no penetration. To fix this, we need to move the ladder back half the distance of the depth of the support, since the penetration is caused by only 1/2. Select the floor fix bone and add a driver to the C value, the way that is back and forth to the bone. Change the default variable to use support depth. Since the penetration is of half the depth, set the expression to var divided by 2. And now the ladder stays on the floor when we change the support depth. No matter if we change the shape or lean the ladder, it never goes through the floor. The 2 bones we have added so far will only be used under the hood and will be hidden at the end to avoid user interaction. So, let's start working on the bones that the user will actually be using to control the placement of the ladder. First, let's add the bone that controls the base of the ladder. Go into Edit mode and add a bone. Let's rename it Base. Let's make it thicker and shorter so it doesn't overlap with the floor fix bone, making it easier for us to select the right bone. If we parent the rotation bone to our new base bone, everything follows it when we move it in pose mode. The ladder is parented to the floor fix bone, which is parented to the rotation bone, which is parented to the base bone. Let's change the maximum draw type of the armature to wire and turn on X-ray so nothing gets obstructed. Next up is the bone that decides what the ladder is leaning against. Let's add another bone and rename it Wall. Make it skinnier and longer to avoid it overlapping with the other bone. And finally, we will add the master bone that will move everything. Add another bone and rename it Master. Let's make it wide and flat so it really stands out. Finally, select the wall bone and the base bone and parent them to the master. Keep offset. Let's go to pose mode. We can move the base bone and the wall bone independently, and if we move the master bone, everything follows. Currently, this looks very confusing with almost no indication of which bone does what. We will fix it later in the tutorial by giving them different shapes, but this will do for now. Now it is time to make the ladder actually lean against a wall. To be able to properly test the ability to lean while we add it to the ladder, we need to adjust a few things in our scene. First of all, let's add a wall to our ground plane so we have something to lean it against. Things are starting to get a bit hard to see, so let's adjust the colors. I'll give the ladder a brown wooden color so it stands out to the background. Let's also increase the length of the ladder to something that can actually reach the wall. And finally, move the wall bone to the wall where it should be so we can see if it works like it should. Now for the actual leaning of the ladder, we are going to add a driver to the X rotation of the rotation bone. First, let's switch from this quaternion rotation mode to something that is easier to work with, like XYZ Euler. Now there's only one value that describes the rotation for each axis. Add a driver to the X rotation. In the expression, we are going to use a math function that calculates angles in right-sided triangles, which is exactly what a ladder leaning against a wall is, if you imagine the wall, the floor, and the ladder as the three sides of a triangle. All we have to do is to feed the function with the height of the ladder and the distance to the wall, and we will get the angle the ladder should have automatically. There are different functions for calculating triangles depending on what you have and what you want. If you want to read up on this, it is called trigonometry, and it is useful for many different situations. In this case, we are going to use a function called asine, and we are going to feed it with the distance divided by the height. Asine, parenthesis, distance divided by height, parenthesis. The expression fails because we haven't created the variables height and distance yet. So let's do that. We will start with the distance. First, let's rename the default variable to distance and then change it from transform channel to distance. Now all we have to do is to select the two things we want to calculate the distance between, and we get the distance. We want to calculate the distance between the wall bone and the base bone, so select the armature as the objects and then those bones. Done. That's how simple it is. Calculating the height of the ladder is a bit more involved, since the height can be very different depending on the look we have chosen. What we will do is to write an expression that uses the values of the controls and calculates the resulting height. Thanks to the controls reflecting the actual size of the ladder, this will be pretty easy. First, let's add the controls that affects the height of the ladder as variables. There are only three: and the distance, step distance, and step count. Now let's replace the height I wrote with an expression that gives us the height using the variables we just created. I will add a few spaces just to make everything easier to read. They don't make any difference. Let's increase the window size so we get some more space. The ladder has two ends, so let's start with end distance times 2. Then we have the steps between the two ends. That length is decided by the step distance times how many of those distances there are. The number of distances between steps is one less than the actual number of steps, so we add step distance times step count minus 1. Press enter and the error disappears. However, the ladder is leaning in the wrong direction, so let's invert it by adding a minus sign in front of everything. Now you can see that the ladder is leaning against the wall, and when we move the wall bone, the angle changes accordingly. When we move the base of the ladder, you might notice that the leaning isn't working perfectly. In the finished result, the ladder was glued to the wall, not moving a millimeter away from it when I moved the base. But here it goes through and away from it in different amounts, depending on how much I move the base. This is due to Blender's order of evaluation. When Blender calculates what should be happening, it calculates things in a certain order. In this case, the issue is that the position of the base gets changed after the angle has been calculated. The angle we see is the angle the ladder should have had the last frame. But for this frame, the angle is incorrect since we have now moved the base of the ladder further. We can fix this by simply delaying the placement of the ladder as well, so it doesn't get moved after the angle has been calculated. So, how do we give the base the same delay as the angle? Since the angle is calculated using a driver, I will move the ladder using a driver as well, instead of moving it with parenting. Go to Edit mode, select the rotation bone, and remove its parent base bone. Now the rotation bone, and therefore the ladder, is completely independent again. However, I still want the rotation bone to be parented to something. Otherwise, it stays in place when I try to move the entire ladder using the master bone. So, instead of having it parented to the base bone, we are going to parent it to the master bone directly. And now the rotation bone, and therefore the ladder, follows it like it should when I pose to master bone. But now, moving the base bone doesn't change anything. So, we need the rotation bone to move with the base bone using a driver. Add a driver to the C location of the rotation bone, the way that is back and forth to the bone. Change the default variable to use the C location of the base bone and to use local space, since we don't want the location of the master bone to affect it. Set the expression to var. And now it is working like it should. The ladder is glued to the wall when I move the base bone. The rotation bone is parented to the master, but also moved back and forth depending on the base bone. We have another issue that we haven't noticed yet. What happens if I move the ladder so far from the wall it can't reach? Let's try and see. We'll slowly pull it away from the wall. Now it is suddenly standing straight up, even though it should be lying flat on the ground. And when we move it back to the wall, it doesn't work anymore. Let's take a look at the rotation driver to see what happened. As you can see, we have an error saying the expression is invalid. This is because the asine function failed to calculate when the ladder was shorter than the distance to the wall. There is no possible solution to that. The ladder can't be leaning on something it can't reach, so the function failed. And once an expression fails, the driver gets stuck with an error. It doesn't start again when the ladder gets close to the wall. If we just go into the expression field again and press enter, it starts working again, because now the ladder is longer than the distance to the wall. But if we move it away from the wall, it fails again. To stop it from ever failing, we have to limit the value we put into the asine function. To the asine function, the distance to the wall can never be longer than the ladder. The actual distance to the wall can be longer than the ladder, but the value the function uses to calculate the angle can't be. If it is, it fails. What we want to avoid is the distance value being bigger than the height value. When the distance divided by height is 1 or higher, it fails. So what we have to do is to make sure that the input into the asine function is always less than 1. The way we are going to solve this is by adding a min function inside of our asine function. That way we can limit the input, stopping it from ever reaching 1. I will add and remove some spaces to make things easier to see. This entire center part is the input for the function. Let's put 2 brackets around it so we can clearly collect it all in one place. This is what we always want to be less than 1. So let's add the min function. Write min bracket in front of it. This entire thing will be the first value we put into the min function. Then add a comma after so we can write the second thing we want to put into the function. 0.9999999999. Super close to 1, but still less than 1. And then finally an ending parenthesis. What the min function does is taking the smallest value of these 2 values. As long as the distance divided by height is smaller than the 0.99, that value will be used. If the distance divided by height is larger than the 0.99, the 0.99 value will be used. We are now limiting the value to always be less than 1. Press enter and try it. When the ladder is too far from the wall, it stays in the lowest position, looking like it drags along the floor. And when it gets closer again, it goes up against the wall. As you can see, by limiting the value, not only did we stop the function from failing, but we actually got the functionality we were looking for all along. By limiting the ladder to its most extreme angle while it is away from the wall, we made it drag along the floor, like we want. What we have done is kind of a cheat, since the ladder never really lies flat on the ground. However, since the angle is so extremely small, it doesn't matter. It is not visible, but it is enough to turn it into a working triangle to the computer, since it has such a high precision. One final issue we haven't noticed yet is what happens when we scale the master bone. Everything is scaled like it should, but we can also see that the angle of the ladder changes depending on the size. Here we can see the importance of using the correct space. The distance variable in our rotation driver uses world space, so when we shrink the ladder, the wall bone gets closer, decreasing the angle. To fix this, we will switch to local space for both bones. And now we can give it any scale we want and the angle remains. Great! Now the ladder is fully functioning, but before we end this tutorial, we will spend some time making it more user-friendly. Let's start by hiding the bones we don't need to see anymore. These are the bones that are driven by drivers and shouldn't be touched by users. Select the rotation bone and the floor fix bone and move them to another bone layer. Now all the bones visible are bones I should be touching as a user. However, it is really hard for me to understand what each bone does by just looking at them. We can fix this by creating custom bone shapes. This is done by just creating normal meshes and then select them as the shape for our bones. I will switch to a separate layer while creating them so nothing is in the way. I will not go into how I am modeling these meshes since it is very basic modeling. However, I will explain why I designed them like I do. For the base of the ladder, I will create 2 arrows pointing in the 2 directions it can move. This way, people understand it can be moved freely, but only along one axis. It is only the edges that matters and will be visible since I have set the maximum draw type to wire for the armature, so I don't fill any faces. Notice how I make the arrow upright. This is because the y-axis is up to our bone. By modeling it like this, it will lie flat on the ground when I assign it as the bone shape. We set it as the shape for the bone by going to the bone panel and selecting it under custom shape. Adjust the scale of the mesh in edit mode to adjust the size of the bone. When we are happy with the result, we can move the original mesh to another layer since we don't need to touch it anymore. For the wall bone, I want it to look like it is supposed to be placed where the floor and the wall meets. Therefore, I will make it look just like that. The meeting of a piece of floor and wall. By pointing the floor towards the ladder, it is clear to the user where it belongs and along what axis it can be moved. For the master bone, I will just give it a simple circle. This indicates that it has no limitations. You can do as you please with it. By making it the largest bone in the scene, you show the user that it is the top of the hierarchy. This is the bone that controls everything else. The lower in the hierarchy, the smaller the bone. Since the wall bone and the base bone has the same level in the hierarchy, both direct parents to the master, I make them the same size. Already this looks like clean and clear controls to me. All bones has a visible purpose, just affecting one aspect at a time, and all of them can be moved without limits that seem arbitrary to the user. Actually, they can be moved too freely. Neither the wall bone nor the base bone should be able to move along anything but one single axis. In your armature, you should always turn off everything that is not used as a control so the user doesn't change things that shouldn't be changed. This can easily be done in the properties panel. Let's lock the scale, rotation and all the location axes but Z for our two bones by clicking on the padlocks. And now they can only be moved along their local Z, or the scene Y. The master bone should be free to be moved and changed any way the user wants, so we will leave it as is. Turn off the ability to select the ladder, so we can't grab and change it by mistake. There is one last issue left, and that is what happens when we move the wall bone the other direction. Since the angle is calculated from the distance between the bones, the ladder starts leaning again when it reaches the other side. The wall bone should never be able to cross the base bone since the ladder will always lean in this direction. To fix this, we will add a limit location constraint to the wall bone and change the location we limit it to based on the location of the wall bone. Add the limit location constraint. Activate just the maximum C and set it to local space. If we now decrease the value of the maximum C, we can push the wall bone further away. So, let's add a driver that does it automatically. Change the default variable to use the base bone, C location in local space, and set the expression to var. Now the wall can't cross the base bone no matter what. If I move the wall bone, it stops. And if I move the base bone, it forces the wall bone back. Now the controls are complete. This concludes the tutorial on creating an automatic ladder. We now have a fully functioning ladder that can easily be adapted with user-friendly controls. I hope you have learned something. Thanks for watching.